Hello everyone. I hope all of you are safe and secure in your respective homes. This video comes at the end of the first week of our quarantine. I hope you all are practicing social distancing and healthy hand hygiene. I'm not really sure as to how long this quarantine would continue. That's why I've decided to record this little video so that you all may be able to study at home. And remember, this is on an experimental basis, so if this comes out well, then I'll be recording more videos in the future for the other lectures. I have provided also a link to this video in our Google Classroom. I have also uploaded the slides in our Google Classroom so that you may be able to download them later and watch them in your own personal devices, or you could take a printout of them if you want. So coming to this particular lesson, in this lecture we shall understand the interesting behavior of complex integrals. The content of this particular lecture is part of module 1 of the Mathematical Physics 3 course. This is the plan of the lecture. I think I had just started the discussion on complex integrals before our classes were interrupted. So for the sake of continuity, I will just briefly touch upon once again here. And then I would introduce a very useful relation called the ML inequality. This inequality is used practically everywhere in complex analysis, especially in proofs of theorems. After that, I would present to you an extremely useful theorem called the Cauchy's integral theorem. This theorem has many practical applications, such as in electric potential theory. This would then lead us to what is known as the Cauchy's integral formula. From the perspective of your course, this formula would help you to easily evaluate many different kinds of complex integrals. Finally, using the ML inequality, I shall derive the Cauchy's inequality, which basically provides an upper bound for the value of the derivative of an analytic function at any point. So without further ado, let's just briefly go through what complex integrals are. So if a complex function f of z is single valued and is continuous in some region R in the complex plane, then we can define a complex integral of f of z between 2 points a and b along some curve in R, and its value will in general depend upon the path taken between a and b. So let's see how this works. So okay, so let us say I have one point here. This is the point A, and another point B over here. This is point B. Now let us say I have one path. There is some function f of z which is defined. Now this is a region, okay. So this, let's say, is this entire thing is the region that we are interested in. This entire area that I have drawn here, this is the region R. This is the region R, and within this region R, let's say that we have these 2 points A and B, and then I take one path from A, and this path, let's say it ends at B. Okay, then what I do is I find out what is the value of the integral of the function along this path. Okay, this let's say this is path number 1. Then I take another path using the 2 points again as just starting and end points. Another path, let's say this point, I call it this path, I call it as path number 2, and again I find out the value of the integral along this path. What happens is the value of the value that I get along path 1 and the value that I get along the path 2, these two values, the integral of the function, these two need not be the same. Okay, so that's what happens in the case of a complex integral. Okay, so the same thing is illustrated here. So I have point A and point B. So we have three different paths, C1, C2 and C3, and in general the integral along C1, integral along C2 and integral along C3, they are not really they need not be the same, but in some cases they can be same. Okay, so now suppose I have a particular path C which is described by a continuous real parameter t, okay, and where the t value of t, now this t is a real number. It has got a lower limit alpha and the upper limit beta, and the successive positions in C are given by the value of x and the value of y as functions of t. So this is what really it means. Okay, so let us say I have a starting point here A. Remember, this is in the complex plane. Okay, so we have a starting point A over here, and then we have an end point, let's say B, also in the same complex plane B. Then let's say I have a path from which takes me from A to B. Okay, let's say I have a path which takes me from A to B. Now at the same time you consider in a number line, okay, a real number line. So this is a real number line, and on this real number line, so we have one point which is here, this point here, we have your alpha. So here we have alpha, and then we have the upper point, upper limit, and this is our beta. Okay, and this axis that we have here, this is that axis t, this is the real number t. So now what happens here is, when this t takes the value alpha, correspondingly we get this point A. Okay, that means, because you see, for each and every point A there is going to be an the real part x and an imaginary part y. So for this value, when t takes the value alpha, the real part will be, the real part, that is x, will be whatever is the x value, the real part of this point A, and the y will be whatever is the imaginary part of this point A, of this particular point A. Now similarly, when t takes the point beta, then this corresponds to this point. Okay, so which means, in general, if I have any point in between on this curve, if I have any point on this curve, this point would, in general, it would correspond to some value of t which lies between, some value t which lies between alpha and beta, and when I substitute in this function of x and y, it will give me this general point. Okay, so in general this could be some point z. Okay, so the integral along C is given by this one. Okay, so now you could, because we have seen that f can be written as u plus iv, and dz, z is equal to x plus iy, so dz is dx plus I dy. So I could just replace this, f of z is replaced with u plus iv, and dz is replaced as dx plus I dy. And now you expand this, so you'll get 4 different integrals. Now we collect the real integrals and the imaginary integrals. So we have the real integrals here and the imaginary integrals over here. Now this dx, because you see this dx is a function of t, right? So that means this integral, it implicitly depends on t. So we want to bring the dependence on t inside this integral. So what you do is, the way to do that is, dx is nothing but dx by dt into dt. Similarly, dy is dy by dt into dt, and here also dy, and here also dz, and we substitute over here. Okay, so for this integral to exist, the sufficient condition is these 4 integrals, they should also exist, all of them. Okay, I mean at least one of these integrals, they should exist. So and when is that possible? That possible is this dx and dy, these derivatives of x and y, they must be continuous. So that's the sufficient condition for the existence of a complex integral. Okay, so now let's take an example. The example is, let's say I have a function. The function is f of z equal to z inverse. I want to evaluate this function along this path. The path is a circular loop. Okay, a starting point is this one, and we go around and we come back to this point. This radius of the circle is r. Okay, so that's the problem. So problem is, again, f of z is equal to z inverse is the function, that is f of z is equal to 1 by z, that is the function. We would like to integrate that function over this closed loop, and this closed loop, it starts at this point, that is z equal to r, and it ends again at z equal to r. So over this closed loop, this we define this parameter t. Okay, this parameter t, in this case we take it to be the argument of this point. Now in this previous slide we had seen this t, right? So the question could be, what is this t? T can be any real parameter. Okay, so we are free to choose any real quantity as the value t, which will give us, which will help us to describe the path. So in this case, the argument of this point, all the points on which lie on this circle, that argument, because argument is always real, so we could take the argument as the parameter t. So this path c can be parameterized as r cos t plus I r sin t, which makes sense, right? Because suppose I take in general any point on this path. Okay, let's say I take this point z here. Z is equal to x plus I y. So what is x? X is nothing but the r cos of this angle, so r cos t, and y, the imaginary part, is r sine of this angle. So this is x and this is y, and of course the value of t, it lies between 0 and 2 pi, because we are going around this closed loop. So at the starting point the value of t is 0, and then when you take one full loop, the value of t will be 2 pi. So now what is f of z? F of z is z inverse, which is equal to 1 by z, and 1 by z is equal to 1 by x plus iy. Why are we doing this? Because we would like to write down the function in terms of x and y, and once we have written it in terms of x and y, we could replace the x and y in terms of the parameter t. So now we don't like to put the imaginary quantity in the denominator. So what you do is you multiply and divide by the conjugate of the denominator, and we get x minus iy divided by x square plus y square. So now we split this up, so we have two terms. One is x by x square plus y square. This is your real part of the function, and this is the imaginary part of the functions. So remember, f can be written as u plus iy. So this is your u and this is your v. Okay, so this is u and this is v. So u is equal to x divided by x square plus y square, and v is equal to minus y divided by x square plus y square. Now what is x? X is r cos t, right? And what is x square plus y square? X square plus y square is r, right? So r cos t divided by r square, which gives us cos t by r, and v is equal to minus y. Minus y is minus r sin t, and again this one is the magnitude, square of the magnitude of the radius. So r x square plus y square is r square, gives us sin t by r. Okay, so u is equal to cos t by r, and v is equal to minus sin t by r, and z is equal to r cos t plus I r sin t. So dz is equal to, just differentiate this one. Differentiation of cos is minus sine, and differentiation of sine is cos. So we have this as dz. So dz is equal to r into minus sine t plus I cos t into dt. So therefore this integral, if you would like to work this out, so what we do is we replace this f of z. F of z is u plus iv, this is f of z, and dz is this entire thing, which is dz. So expand this, so we'll get minus sin t cos t plus sin t cos t, which these two will get cancelled, so which will leave behind this. Okay, so I integration of cos square t plus I sin square t. You could also do it another way, because sin square plus cos square is 1, so we have I pi plus I pi. Okay, or another way is integration of cos square is pi over 1 full loop is pi. Same thing goes for sine, or you could just add them together. Sin square plus cos square is 1, so that will leave us only t, and there is an I here, so integration of t over from 0 to 2 pi is going to be twice pi I. So that is going to be the solution of this particular complex integral. Now properties of complex integrals. First property is the linearity. Suppose I am having two functions f1 and f2, and these two functions are multiplied by two constants k1 and k2. Remember, k1 k2 here could be complex numbers, it need not be real numbers. Then this is equal to, you could just split them up like this, and the constant k1 multiplied with the first integral plus constant k2 multiplied with the second integral. This is the linearity property. Then sense reversal. So suppose you start your starting point is z0 and the end point is capital Z, and you try to integrate this function f of z. Then if I come back to the same path in the opposite direction, right? So that means from starting point is z0 and end point is starting point is z and ending point is z0. Then if you come along the same path, then the result of the integral will be, you have to put a minus sign, that is sense reversal. And partitioning of paths. So suppose I'm having a path C, and this path C is made up of two paths C1 and C2. So say we have a scenario like this. So we have one path, this is the entire path. So this is the entire path. This is your path C. This is the path C, and let's say this path C you partition into two parts. Okay. So this is the first part. This part is, let's say, C1, and this is the second part, which is C2. Okay, so this is the total path, and the total path I have partitioned into two parts, C1 and C2. Then the integral over the total path, the integral over this entire path is equal to integration over this path plus integral over this path. That is the partitioning of path. Okay, now coming to the ML inequality. Okay, now this ML inequality, it provides an upper limit on the estimate of the absolute value of a complex line integral. So suppose I have a function f of z, and m is an upper bound on the value of f of z on a given path, which means suppose you have imagine a path, okay, and as long as you're moving along this path, let's take this, okay, suppose I have a path C, and you're moving along this path. As long as you're moving along this path, the value of the function, it does not exceed a value m, that is the magnitude of this function does not exceed a value m. And suppose you also find out what is the total length of this path. Let's say the total length of this path is L. Okay, then what will be the magnitude of the integration of this function over this entire path? So now magnitude of the integral is less than equal to magnitude of f into magnitude of z. We get this result from this because if I have two quantities, the magnitude of the product is less than equal to the product of their magnitudes. So now what I do is, if I replace this, because we know as long as you're on this path C, this function will take a value which is always less than m. So I could just replace this with m, and it will be guaranteed that this integral will be still less than equal to. Okay, so this less than equal to will remain. Now m is a constant, so m can come outside the integral, so we have m. And then what we have here is we have integration over of dz, modulus of dz over C. Now this is nothing but a segment, a small segment on the path, and you are integrating over the entire path. So this is going to give me the length of the path, the total length of the path, which is ml. So this gives us the magnitude of the line integral over a path C is less than equal to m times L, where m is the upper bound on the magnitude of the function and L is the length of the path. So that is your ML inequality. Extremely useful result, which is used almost everywhere, okay, in various proofs in complex analysis. Now coming to the Cauchy integral theorem. Okay. So suppose I have a function f of z which is analytic on some domain D, and f prime z is continuous at each and every point within and on a closed contour C inside D. Then the closed loop integral of the function f over the C is going to be always 0. So that's your Cauchy's integral theorem. So to understand this, so let us say I have a certain domain. Let's say this is a certain region in the complex plane. This is my domain. Okay, so this is my domain D, so which means the function is analytic everywhere on this domain. Okay, now if I take a closed loop inside this domain, okay, I have to ensure that the loop is closed and it lies totally inside this domain. So let's say I have a closed loop C which lies inside this domain. Now I cannot take a domain, I cannot take a closed loop like this. Okay, I cannot take a closed loop like this because this loop, this part of this loop, it does not lie inside the domains. Okay, so the loop, it should lie totally inside the domain. Okay, then what the Cauchy's integral theorem says, this because the function is analytic over this entire domain, which means, and this loop C is lying totally inside this domain D, that means the function f of z is analytic at each and every point inside C, because C lies totally inside D. Okay, so that means all the points which are in the interior of C, they are also points of D, and the function is analytic in point D, so the function must also be analytic on the points inside, and the function is analytic on all the points on the contour C. Then the Cauchy integral theorem says that if this condition is satisfied, that the function is analytic everywhere inside this C and also on C, then the closed loop integral of this function over this contour C, that will always be 0. So now we have two corollaries to the Cauchy integral theorem. The first corollary is basically this. So suppose I have 2 points A and B in the complex plane, and these are joined by 2 different paths C1 and C2. If f of z is an analytic function on each path and within the region enclosed by the paths, then the integral of f of z is the same along C1 and C2, which in other words what it says is, if the function is analytic, the line integral of that function within a domain in which this function is analytic, the line integral becomes independent of the path. Okay, so as long as the endpoints are the same. Let's see how this happens. So I have this point A and B. C1 is one path and C2 is another path. From the Cauchy integral theorem, because this function f of z is analytic, the line integral along over C1 is equal to the line integral over C2. So it really does not matter which path you take, provided the 2 points, the endpoints are the same. Now this will be valid only in case of the function being analytic. If the function is not analytic, then this need not hold good. So how do we prove this? We can prove it very easily. So what you do is we take a closed loop. Let's say I take a closed loop C, okay, and the function is analytic in the interior of C, and it is analytic over the also on the boundary, this boundary C. Okay, so the function f is analytic everywhere. So as per the Cauchy integral theorem, okay, the line integral of this function over this closed loop must be 0. Okay, let's call this as equation number 1. Now what we do is we take 2 points on this path. Okay, this, remember, this was a closed path. Now we take 2 points here. We take 1 point here and another point here, points A and B. Now what does this point A and B, what does it do? It partitions the closed contour into 2 open paths. One is a open path C1, another one is a open path C2 star. Okay, so it divides the loop C into 2 segments, C1 and C2, so that this C, the original loop C, is nothing but a combination of C1 and C2 star. Okay, now by one property of a complex integral that we have seen was partitioning of path, right? So by partitioning of path, the value of the integral will remain the same. That is, integral over this closed loop is the same as, is equal to integral over C1 plus integral over C2 star. Okay, so this was the over the closed loop, this was what we had, right? Integral over C was equal to 0, so integral over C is equal to integral over C1 plus integral over C2 star. Now we're going to use the path reversal property. Okay, so what we do is this C2 star will reverse the path and we'll make it as C2 pointing in the other direction. Here C2 star is pointing from B to A. Now we'll make it point from A to B, because we have reversed the path. Okay, so C2 is equal to minus C2 star. So by path property, we know that C2 star, integral over C2 star is equal to negative of the integral over C2. So now you use this equation number 3 in equation number 2. Okay, so this is nothing but minus integral over C2. Okay, which is equal to 0, and then bring this on this side. So this gives us the required proof for the corollary 1. Now coming to corollary 2. Suppose I am having two closed contours C1 and C2 on the complex plane having the same sense of direction. That means both of them are either clockwise or both are anti-clockwise. Then if a complex function f of z is analytic on C1 and C2 as well as in the region enclosed by the contours. So let's say this is C1 and this is C2. The function is analytic in the region enclosed by them as well as on the boundaries C1 and C2. Then the second corollary, what it says is the closed loop integral over C1 must be equal to the closed loop integral over C2. Okay. So what we can do is we can prove it very easily by reversing the direction of the inner contour. So what we do is this C2 will just reverse it. It was going in the anti-clockwise direction. Now we'll just reverse it to be in the clockwise direction, and with this clockwise direction we'll call it as C2 star. So again, by the reversibility of path property, we know that the line integral of over C2 star, it must be equal to minus of the line integral over C2. Okay, so now what we do is we take a small cut. Okay, now you see we can't directly use the Cauchy integral theorem and say that okay, this will be equal to 0, because for the Cauchy integral theorem it should be analytic at all points within. So I cannot simply say that the line integral over C1 is 0 and the line integral over C2 is 0, because all that we know is the function is analytic in the region between them. We really don't know what happens over here. The function may not be analytic in this particular area. Okay, because that is the case, so we cannot really set this to be equal to 0. So now what we do is we make a small cut here. Okay, anywhere you can make a cut here. So what we do is we will make two small cuts. One cut we call it as L1 and one cut we call it as L2, and we'll say that these two cuts are very close. These two segments are very close to each other. Okay, so because these two cuts are very close to each other and they are in opposite directions, so we may safely say, because they are infinitesimally close, the integral over L1 must be equal to my negative of the integral over L2, because they are very close to each other and it's like going along the same path but in opposite directions. So the integral over L1 and L2, they will be opposites of each other. Okay, so now you've observed this. Okay, earlier what was there? We had two boundaries, right? We had one boundary, outer boundary, one inner boundary, C2. Now we have reversed C2 and we got a C2 star and we put two cuts. Now you see this boundary, it has become one single boundary, because you see you start from L1. Okay, you start from L1. Okay, then you go around C2 star and then go along L2 and then go along C1. We come back to the same path. Okay, it's the same continuous path. So C1, C2 star, L1 and L2 together form a closed loop, and let's say we call that closed loop as C. Okay, so integration over L1 plus integration over C2 star plus integration over L2 plus integration over C1. This must be equal to the closed loop integral C. Okay, so using these two equations, this equation number, okay, this equation number 1, equation number 2, in this particular equation number 3, when we use this, then what happens? These two, they are opposite of each other. So L1 is equal to minus L2, and we had C2 star, which is equal to minus C2. Okay, which is what we had here. So now these two will get cancelled out. This first and the third integral will cancel out, so which will leave us this one. Okay, now integral over C1 must be equal to integral over C2. Why is that so? Because this is going to be equal to 0. Why is it 0? Because you see, this is the complete closed loop. The function is analytic at all points on this total closed loop C, and it is also analytic everywhere. So that means over this closed loop C, the Cauchy's integral theorem is valid. So by Cauchy's integral theorem, because it is analytic in the interior and it is analytic on this closed loop C, so this is going to result to 0. So as a result, we have this, which completes the proof for the second corollary of the Cauchy's integral theorem. Okay, so I think we'll take a break here, and then in the next part we will look at the Cauchy integral formula and eventually end with the Cauchy's inequality. Thank you.